So, this part of Schwartz's book is striking me as being full of typos, and some of them are pretty serious. Let me pick up from where we were last time. We were talking about doing renormalization in a systematic way, and we basically had I G of P slash. We wanted it to be I P slash minus M plus I epsilon plus terms that are regular at P squared equal to M, P slash equal to M. And moreover, we had gamma mu at 0. We wanted that to be gamma mu. And we also wanted pi of 0 to be 0, which gives I G mu nu. This is the photon propagator. This is the electron propagator. This is then minus I eta mu nu over P squared plus I epsilon plus P nu terms. And of course, these would be gauge dependent, and then possibly something that's regular at P squared equal to 0. So those were our renormalization conditions. And there are different ways of accomplishing this depending upon what your scheme is for regulating the infinities. And we had in dimensional regularization with minimal subtraction. This is called MS bar. We had delta 1 equal to delta 2 equal to E squared over 16 pi squared times minus 2 over epsilon. These are the counter terms, of course. And delta 3 was E squared over 16 pi squared. So for things that are renormalized, I'm just leaving off the capital R because it just makes things too confusing. It was this times minus 8 over 3 epsilon. And we were saying if we're in 3.9 dimensions, then epsilon is about a tenth. So this is like minus 20, and this is minus 80 over 3, I guess. Times the factors in front. The factors in front, of course, are very small because this is 1 over 137, and this is pretty small as is that. I mean, 1 over that. And we had delta M as E squared over 16 pi squared, and then this was minus 6 over epsilon. And we also had the pi 2 of P squared was E squared over 2 pi squared into the along the x1 minus x log mu squared over m squared minus p x1 minus x, that's p squared x. Mu here is called a subtraction point. And that's actually the formula that we got just from saying, well, let's not compute the thing, but only its derivative, and then integrate from some measurable point. Now, what we saw also was that in both dr and polyvolars, we have delta 1 equal to delta 2. And what that means, of course, is that Z1 is equal to Z2. And we had also defined Z1 as ZE Z2 square root of Z3. I'm very uncomfortable with formulas like this, but let's go on. So if Z1 is Z2, then we have 1 is Z2, is ZE square root of Z3. On the other hand, ZE is defined as E0 is ZE times E. So this is the Coulomb's electric charge. This is the renormalized one, and it's being multiplied by CE. And so what we see then is that E, which by definition is E0 over ZE, this is square root of Z3 times E0. On the other hand, Z3 originally came from setting A0 mu equal to square root of Z3 A mu. That was our original definition of Z3. So what we see here is that there's a certain quantity that doesn't get renormalized, namely EA mu, which is then E is square root of Z3 E0. And A mu, well, A mu is A0 over square root of Z3. So EA mu is E0 A0 mu. So that's interesting. And it means in particular that the covariant derivative that might start out as d mu plus I E A mu, and it might start out in one Lagrangian with zeros, is the same thing as d mu plus I E A mu. And this is the key thing that's involved in gauge invariance, because you remember the way one does gauge invariance is we say d mu psi prime should be e to the I alpha q d mu psi, where psi prime is e to the I alpha q psi, where alpha can depend upon space-time, as does, of course, the field. And so this is saying that d mu prime should be e to the I alpha q d mu e to the minus I alpha q. And in fact, the way I think of it often is that I actually have the E in here and then some number. And so, well, anyway, the point is that that the fact that this thing doesn't get changed it's quite significant, and it's got to do with gauge invariance. And the gauge invariance of the renormalization procedure. One way of thinking about it is to write the original Lagrangian, to imagine that we have two charged particles. We have electrons and positrons, and also, say, the up quark and the anti-up quark. And in that case, what we have is a quarter Z3 F mu nu plus I Z2E, I wonder whether I should just combine, well, all right, I'll write the whole thing out. Psi bar E D slash psi E minus E Z1E psi bar E A slash psi E. So this is Z1, E means of the electron. So we should make this a smaller E in this. And then there's another term for the up quark, Z2Q psi bar Q D slash psi Q minus, and now this will have charge 2/3, so this is plus 2/3 E Z1Q psi bar Q A slash psi Q. So we can rewrite this as minus a quarter Z3 F mu nu F mu nu, and now combining these things we get plus Z2E psi bar E I D slash minus Z1E over Z2E E A slash psi E. And then we get here Z2Q psi bar Q I D slash, this is the covariant derivative basically, plus Z1Q over Z2Q 2/3 E, notice the change in sign here, A slash psi Q. Okay, so what we've got then is, if these cancel, and not only do they cancel, but they cancel for both fields, then we've got a nice Age Invariant theory. And the idea is that when we start out without any renormalization, we just write the theory at tree level, or write it classically. There we have gauge invariance. We then have a gauge invariant renormalization scheme, so it's reasonable that we preserve gauge invariance, which means that these things, at the very least, this ratio for E has to be the same as for Q. But even better, in fact, if it's the same gauge invariance, then these guys both have to be 1. All right, let me now just go through a few things about the Ward identity, but Schwartz goes on to argue that he can actually go a little further with this argument about Z1 and Z2. I'm not going to go the whole distance. I'm just going to go through a little exercise here, just because it will maybe sorry, that was a con, and then I thought it was P1. Okay, let's look at what this is. The Ward identity gives us this is M0 Q1 plus P Q2 minus M0 Q1 Q2 minus P. And what's M0? Well, M0 of Q1 and Q2, it's an integral d4th x1, d4th x2, e to the I Q1 x1 minus I Q2 x2, and then the 2-point function, like that. What we can do now is write this in terms of as a Fourier transform, in other words, in terms of g of p slash, which was the very first thing I wrote down. In other words, this is d fourth x1, d fourth x2, e to the I, q1 x1 minus I, q2 x2, and now the rest of this is d fourth q over pi to the fourth, and if I took away the I, so this is just g of q slash. And, oh, sorry, it's g of q slash times e to the minus I q x1 minus x2. Okay, now we can look at this d fourth x1 integral. We've got e to the I q1 x1 and minus I q x1. And if we absorb the 2 pi to the fourth, we see that's a delta function. So that gives us d fourth x2 delta of q1 minus q times e to the I x2 q minus q2. So that's q minus q2. And we still have the d fourth q, and then we have g of q slash. And so doing the q integral just gives us q. The delta function tells us that this is just d fourth x2. Q is equal to q1 because of the delta function. So this is q1 minus q2 g of q1 slash. And now this thing is again a delta function. And so this gives us 2 pi to the fourth delta of q1 minus q2 times g of q1 slash. Okay. So I just think that it's good for you to see how these things work. Okay, so that's M0 in general, and so this identity here gives us 2 pi to the fourth delta fourth, and the first term is then q1 plus p minus q2 g of p slash, and in other words it's whatever q1 was, so it's p slash plus q1 slash, and then the other one has q2 to be q2 minus p, and so this one is minus 2 pi to the fourth delta of q1 minus q2 plus p. So now you see they're the same delta function. It's just the p is in a different place. And what's left is g of, well, it's q1 slash, and it doesn't depend upon q2, so it's just q1 slash. And so altogether this thing is 2 pi to the fourth delta fourth of q1 minus q2 plus p times g of p slash minus plus q1 slash minus g of q1 slash. Okay, all right, well, Schwartz goes on with that. I'm going to stop there, though, for that chapter. Now go on to the infrared divergences. So the basic idea here with the infrared divergences is something that is much more appealing and understandable than the ultraviolet divergences. And I think one can say that the treatment, I'm not sure what the best treatment is. I would think something involving coherent states would be the right way to do this. And I suppose by now somebody has done that. In fact, let me assign a homework problem. The homework problem is to Google the literature and see if you can find a treatment of these infrared singularities in terms of coherent states. So that might be a nicer treatment than the treatment that I'm going to sort of outline that Schwartz does. So that's a sort of weird homework problem, but it's kind of a modern homework problem. Might be more fun than, well, certainly more fun than the trace problem. All right, so the basic idea is that photons are massless. So low momentum photons, infrared photons, are cheap. And consequently, if you have any sort of a scattering process where charged particles are colliding, producing charged particles in the final state, well, it's kind of silly to compute the cross-section for, say, E plus E minus goes to mu plus mu minus, and completely ignore the photons in the final state. Because, in fact, you can't really measure the E plus E minus goes to mu plus mu minus, because you're never sure there isn't some soft photon there. 3-degree Kelvin, for God's sake, right? I mean, something, you know, would be swamped in the background radiation. You wouldn't even see it. Okay, so that's basically the idea. And what one does then is, so technically, what one does is one computes cross-sections, and in fact, cross-sections for processes, that for sums of processes. And in fact, there's a general name for these, namely they're called inclusive cross-sections. And so it's, for example, cross-section A goes to B plus X, where X can be anything. And that's not what we're doing here. We're saying what we would like to do here would be cross-section A goes to B plus any soft photons. That's what we would like to do. Instead, we're going to do cross-section E plus E minus goes to mu plus mu minus plus the cross-section E plus E minus goes to mu plus mu minus plus one soft photon. And it turns out that that's enough to cancel the infrared singularity. All right, so let's start this procedure then. And what we'll find out is that sigma E plus E minus goes to mu plus mu minus plus sigma E plus E minus goes to mu plus mu minus gamma, soft gamma. It'll turn out to be sigma 0 times, and this will be the correction, 3e squared over 16 pi squared. So what's sigma 0? Sigma 0 is the tree level value of this cross-section. And this is something we computed last semester, namely it's e to the 4th over 12 pi q squared. And I think actually that it probably is only this simple in the limit of pi q squared. Q, what's Q? Q here is energy, is center of mass energy. All right, so let's remember how we computed sigma 0, or at least recall it to some extent. I m 0 then is, it's the P1, P2, so this is electron photon going across muon P3, anti-muon P4. And so you get a photon propagator, and then you get some spinors, E squared or Q squared, V bar of P2, gamma mu, U of P1, U bar of P3, gamma mu, V of P4. Okay, so let me just point out how this goes, just so that you remember it a bit better. For the electrons and the muons, the particles as opposed to the antiparticles, if its initial state appears as a U, if its final state is a U bar. So that's U bar there. And this is U. U. On the other hand, for antiparticles, it's the opposite. If it's an antiparticle, then in the initial state it's a V bar, and in the final state it's a V.
Hi, sorry.
You want to get a coffee too? All right. So as I was just reminding people, well, let me just give you the quick summary. In infrared divergences, the way to cope with them is much more physical and mathematically sensible than with ultraviolet divergence.
Okay.
With ultraviolet divergence, we really don't know what's going on at short distances, so we are inevitably fudging at some level. On the other hand, with infrared divergences, we know what's going on at low energies, and the insight is that because photons are massless, when you have charged particles scattering, you never know how many very low energy photons there are, and you can't really measure them. And so what you have to do is you have to compute things that are the cross section, for example, for E plus E minus goes to mu plus mu minus, plus the cross section E plus E minus goes to mu plus mu minus, plus a soft gamma.
Okay.
And just to indicate how absolutely impossible it is to measure this thing, imagine that the gamma is of the order of 3 degree Kelvin. So it's swamped in the background radiation.
Yeah.
You can't even see it.
Okay.
So that's the basic physical insight. That's the good part. The bad part is that technically these computations are very complicated, and so I'm going to basically skip parts of it. All right, now let's recall, the first thing we have to compute though is this, and so we have to compute the lowest order diagram for this. And the lowest order diagram is that. There's the amplitude, and something that I just mentioned now to the students who actually came on time, is that if you have a particle as opposed to an antiparticle, in the initial state it's a U, final state a U bar. But if you have an antiparticle, in the initial state it's a V bar, and in the final state it's a V. Where, of course, these should be the correct spinors as opposed to the short spinors. All right. Okay. And this cross section, at least at high energy, is e to the 4th over 12 pi q squared, where q is the center of mass energy. Now, in fact, we saw Schwarz's 13.78 that d sigma d omega was e to the 4th over 64 pi squared q squared 1 plus cosine squared theta. So this is the scattering amplitude, say, of the mu relative to the electron. And it's of this, again, for Q going to infinity. This Q squared, by the way, Q is E, Q squared is P1 plus P2 squared, which is the same thing as S, and it's also the same thing as the center of mass energy squared. Okay. So there we are. What is sigma zero? Well, sigma zero of Q squared then is integral 0 to 2 pi d phi integral minus 1 to 1 d cosine theta d sigma d omega, and this is then e to the 4th over the 12 pi Q squared, which is what I quoted at the beginning. So that's sigma zero. Okay, now as we go to higher order, where we are going to encounter, as we go to higher order, we encounter UV and infrared divergences. The UV divergences we renormalize in the same way as we've been doing in the past. And so let's do that part first. That part technically is the easy part. It's Im gamma is then P1, P2, a P goes across. So this is the thing, P3, P4. Okay, so that's the picture. But then we add in the counterterm diagram, which is the same thing, but we've got this infinite term here canceling the infinite term there. Or if we're in 3.9 dimensions, then we have something to the order of 10, canceling something to the order of 10. Okay, so this thing, when you add the two together, we can say is Im gamma, and that's going to be then I E squared over Q squared. And so it's going to look like this, but the gamma mu is going to be replaced by a serious gamma mu. By the way, there are other vertex corrections, but which have UV and IR divergences, but are require one to, I guess, compute other diagrams, such as gamma E plus E minus goes to mu plus mu minus plus this one, if we were going to have the loop over here. And, okay, so we're leaving out, we just want to show that the IR here cancels with a certain, if you add in a certain soft photon. So this is then V bar of P2, gamma mu, U of P1, U of P1. And then U bar of P3, gamma mu 2 of P, V of P4. And of course, P is P1 plus P2, that's P here. And so what we've got here, this is the vertex correction. Remember when we were doing the magnetic moment of the electron, we analyzed this diagram. And what we saw was that there was a UV piece that had to do with charge renormalization. But then if we wanted the magnetic moment of the electron, we looked at the F2 piece, and that was UV finite. Okay. And P squared here is Q squared. All right, now remember that gamma has to be of the form F1 of P squared gamma mu plus I sigma mu nu over 2m p nu f2 of p squared. And we found that f2 of p squared was e squared over 4 pi. By the way, there are some typos in the 18 and 19 that are on Schwartz's typo page, and I didn't check them before I lectured yesterday or the day before, and so I didn't put them in. Anyway, they're things, they're not big deals. They're, well, anyway, they're there. So we have integral 0 to 1. I'm just going to call this d cubed r. Delta of x plus y plus z minus 1. Okay, rather than write dx, dy, dz. And then we have z, 1 minus z, m squared over 1 minus z squared m squared minus xy p squared plus higher order terms. And so if we look at this, we see that as p squared goes to infinity, this goes to 0. And so we just say f2 p squared goes to 0 as p squared to infinity. Okay. And we're in fact looking at the high energy limit anyway, because we wanted to deal with this process, a simple formula for this process, rather than something that was really pretty complicated. Okay. So we're going to forget about it, f2. And one reason why f2 is 0, one way to think about it is that because we've got two gammas here, in between a v and a u bar, that's coupling left-handed to right-handed spinors. And if you look at the normal Lagrangian for massless QED, or equivalently, look at the action for QED and just imagine you're at very high energies, then you can absorb the mass. And so what you've got is something like psi bar d slash psi. And so that's I psi bar gamma mu d mu psi. And so you've got two gammas. And if you have two gammas, well, of course you don't have a bar here, this is a dagger. If you have two gammas, you don't, or let me put it this way, if you have two gammas, then the thing is of the form something, 0, 0, something. And so the left-handed and the right-handed spinors, if they look like that, they don't mix. And I think the reason why this is the case is that gamma 0 is essentially 1, 1 with a possibly minus sign. This is 0, 0, sigma, sigma. And so you see this thing is sigma, sigma, 0, 0. So that's basically what's happening in, well, close enough for something like, right? Okay. So we're not mixing the left and the right hand. And so at high energy, and consequently, since this is part of QED, at high energy this can't contribute. And notice that it's trying to contribute because it's got a p nu here, but this is 1 over p squared. So still p nu f2 still goes to 0. All right, finally finished with that. Now comes the hard part. Remember that we had f1 of p squared was 1 plus f of p squared plus delta 1 plus higher order terms. And we had that f of p squared was e squared over 8 pi squared integral 0 to 1 d cubed r delta of x plus y plus z minus 1 d cubed r plus b dx dy dz. Okay, now that's all multiplied by log z lambda squared. So this is Pauli Villars, as you can see, because we've got a capital lambda there, rather than our trusty 1 over epsilon. So this is p squared 1 minus x 1 minus y plus m squared 1 minus 4z plus z squared over delta. And what's delta? Delta is 1 minus z squared m squared minus xy p squared plus z, and now we stuck this thing in to avoid the infrared singularity. Where's the infrared singularity? Well, the infrared singularity is when p squared is positive, m squared is positive, and so you can have 1 minus z squared equal to xy. In fact, it's when x equals y equals 1 minus z. That's an example of where you have the singularity. And for that case, it's an on-mass shell singularity because you want p squared equal to m squared. And actually, now that I think about it, we're going to the limit where p squared is huge. Well, maybe it still occurs because you can have, if p squared is huge, you can have x and y both near 0. Okay. So it's still totally of course, that couldn't be. Anyway, okay, now, if we imagine this, well, let's just say that our renormalization condition is f1 of 0 equal to 1, and consequently, this delta 1 has to cancel anything that's singular in here. It cancels the ultraviolet part. Now, here is something inconsistent. Delta 1 equals minus f of 0 then. That makes sense. But then Schwartz writes that's equal to minus e squared over 8 pi squared 1/2 log lambda squared over m gamma squared. And that makes no sense at all because it's, well, it might be right, but it's inconsistent with the previous equation. And that's inconsistent with 1959. And so one of the two equations is wrong. And I don't know, I did not, I mean, one can figure out which is wrong by basically using Mathematica to do these integrals and seeing, and I didn't do that. And I sent him, though, an error report. See if what he does with that. Anyway, the reason is that you see delta 1 from 1959 is minus e squared over 8 pi squared 1/2 log lambda squared over m squared plus 9 over 4 plus log m gamma squared over m squared. So here the lambda squared and the m gamma squared are coming in with the same sign. Here they're coming in with opposite signs. And so I don't know which one is right. In any event, modulo typos, what Schwartz finds is that fq squared plus delta 1, so this is the renormalized thing, is equal to e squared over 16 pi squared minus log squared of m gamma squared over q squared minus 3 plus 2 pi I log m gamma squared over q squared plus pi squared over 3 minus 7 over 2 minus 3 pi I plus order m gamma, and we're imagining, and of course m gamma is supposed to be 0, so we don't need to keep that. Okay, this thing here is a squared log, and people call that a double logarithm, and they associate with it with the name of the Sudakov or something like that, which sounds like a pork chop. All right, anyway. In any event, what Schwartz gets eventually from the for the vertex cross section is that sigma v. He gets it to be 2 sigma 0 times f of q squared plus delta 1, and that this is equal to e squared sigma 0 being the tree level e plus e minus goes to e plus b minus cross section over 8 pi squared times minus log squared and gamma squared over q squared minus 3 log and gamma squared over q squared minus 7 halves plus pi squared over 3. All right, so that's the vertex correction. Now, if you add in, so we've got these bad terms here, but if you add in the cross sections for the production of a real photon, a soft photon in the final state, then you've got these graphs. IM is this thing, P1, P2, photon goes across, P3, photon comes out, P gamma, P4, plus, of course, there's another one here. And notice these are tree level diagrams, so these are actually finite. So there's no need to screw around with ultraviolet renormalization. Let me get, does anybody have a question? Let me have a drink of water. All right, and we're, for simplicity, going to this limit, q squared going to infinity, or at least much bigger than the square of the electron or muon mass. Then what we get is that this thing is equal to I e squared over q squared, b bar p2, gamma mu, u of p1, u bar of p3, s mu, v, s mu alpha, I should say, v of p4, epsilon star alpha. This thing has polarization label alpha, where S mu alpha is minus IE gamma alpha I over P3 slash plus P gamma slash. So that one is this one here because this is P3. So this is gamma. So this thing here is that one. Minus gamma mu I over P4 slash plus P gamma slash gamma alpha. Okay, so that one is this one. So the two add in that way, and there's apparently a relative minus sign there. Okay. One finds that the unpolarized cross-section, which of course makes sense since we're saying we can't measure the photon at all, so let's not screw around with its polarization. What one gets is 1 over 2q squared, an integral d product of the that abbreviation LIPS, and I've been writing it as LIPS so long that I can't remember what it stood for.
Or it's invariant phase space.
Bravo! All right, here, I'm gonna,
Very good.
Yeah.
you really should get 2 of them, so let me give you 2 of these. Well, here, that. All right, Lorentz invariant phase space. M squared, and this is
Something wrong. No one can throw in this room.
whatever.
It's not just you.
So this is R for the real emission or radiated, and that turns out to be e to the 4th over 2q to the 6th L mu nu x mu nu. All right, and maybe I'll write L mu nu here. L mu nu is a quarter sum over the E spins, so I'll write that as electrons spins. That's what it is. V bar P2 gamma mu U P1 V bar P1 gamma nu V P2. And you remember that when you sum over all of the spins, this thing turns out to be a very nice expression in terms of gamma matrices and the mass. And in fact, at these energies, we might as well blow away the mass. And I think that's what Schwartz did, because he gets the very simple expression, a quarter trace P2 slash gamma mu, P1 slash gamma nu. And of course, there aren't any masses there, so we're blowing away the masses because we're at high energy. And this thing turns out itself to be P1 mu, P2 nu plus P2 mu, P1 nu, minus a half q squared eta mu nu. And we should keep in mind that the sum of the photon polarizations, E alpha, E beta star, this turns out to be minus eta alpha beta. So that means that the x term, as opposed to the L term, is x mu nu integral d product Lorentz invariant phase space sum over muon spins and the epsilon. That is to say, this alpha here, using that, what you get is, well, you start out with U bar of P3, S mu alpha, V of P4, V bar of P4, S beta nu, U of P3, times E alpha E beta star. And once again, we have, if we sum over these spins and polarizations, this turns out to be that very nice expression. In other words, we get the trace. And this thing turns out to be minus d pi ellipse, can't resist, trace, d3 slash s mu alpha, d4 slash s alpha nu, and d ellipse is, or d pi ellipse is product j equals 3, 4, and then whatever the gamma one is. So an integral over all the final state momenta, d cubed pj, 2 pi cubed, 1 over 2e j, I don't know why you wrote pj, all right, ej, so these are the final state energies, and then an overall 2 pi to the 4th delta 4th of p minus p3 minus p4 minus p gamma. So this is the final state. This is energy momentum conservation, that whatever the p is that comes through here has to be the sum of this and that momentum. Now, using our word identity again, which I never thought was quite well explained before. We have P mu L mu nu equals P mu X mu nu equal to 0. And so X has to have a particularly simple form. Well, it's got a pretty simple form already, and but we have to combine it with the S's. And remember that the S's are these things with gammas. So this, actually, I don't even see why we need to invoke the word identity. You can just compute what the thing is. But in any event, one gets X mu nu is P mu P nu minus P squared eta mu nu. So this satisfies the ward identity. Times some x of p squared. And a similar formula has to hold for L. And the result is that x mu nu, L mu nu, summed over mu nu is minus q squared over 3 eta mu nu x mu nu. And then the total radiated cross-section, at least at high energies, turns out to be sigma r is, we're running low on blackboard space here, but let me just say it's minus e to the 4th over 6 q to the 4th eta mu nu x mu nu. So this is the radiated one. And then that can be rewritten as sigma 0 times minus 2 pi over q squared eta mu nu x mu nu. Okay. All right, sigma 0 is e squared over 12 pi q squared, as we've seen. And, well, I'm out of blackboard space and nearly out of time. Let me say what the final result. This is rather obviously a very technical. I say obviously. I've skipped a lot of stuff. If we'd gone through all of it, you would appreciate that this is a very technical computation, even though the mysterious part isn't there, the UV part. Instead, it's just all IR. What you find if you do everything is the following. You get that the total cross-section, which is the lowest order, well, that's finite anyway, plus radiator, plus vertex contribution. It turns out to be lowest order times 1 plus 3e squared over 16 pi squared. All right. And so in other words, the m gamma terms, which we put in there to cancel the infrared singularities, those guys are not actually there. And I mean, they cancel. When you are computing something that is observable, which is to say the total cross-section for E plus E minus goes to mu plus mu minus, plus maybe some very short photons that you can't observe. And as I said, I think there must be somewhere in the literature a nice treatment of this using coherent states. And so I assigned as a homework problem to Google the literature and see if you could find such a thing. And you wouldn't necessarily just use Google. You might go to the archive and look for something, I'm not quite, infrared singularities in coherent states. It's also, Slack runs this, something similar to the archive. It's older than the archive, but for some reason I always go to the archive rather than to the Slack database. I found the archive easier to use than the Slack one. But it's a question of what you're used to. All right, I think, I don't know, do you think we should skip now to the standard model, or?
Yeah.
Okay, what do you think?
Sure.
I'm good.
All right, let's do that. Another reason for doing it, apart from the fact that this stuff gets more and more technical, is that they're going to turn on that LHC in a couple of weeks. And who knows what they're going to see. So it may be that we should fit in a week or two about the LHC in the very end of the semester. In other words, late April, early May. And they may discover supersymmetric particles. They may discover something totally unexpected. And I don't know what I'm going to, well, it will be speculation. I mean, if they discover something totally unexpected, then there'll be speculation about that, and we can talk about it. If they discover supersymmetric particles, then it's essential that we say something about supersymmetry. So we'll leave time for that. Then. All right, so we'll start that next time. I also discuss gauge theory a little bit in my book, and I think those chapters are available either on the web page for this course or on the web page for 466, 467. You know, the book isn't about the standard model, so I don't focus on it, but when I do group theory, I talk about it, and then when I do tenses, I talk about it again. Well, I guess we can start.